Welcome to this lesson in our linear algebra study. So I'm going to talk about vector spaces, but before we start, I want us to go through something called fields. Okay, so what is a field then? A field is a set F along with two binary operations, and that is addition and then multiplication, for which if you have two elements x, y, okay, in that field, or you can use a, b if you want, then when you sum them, you can do it x plus y or y plus x, and that should be in the field F. And then if you multiply them, they should be in the field F as well. And then if you have all elements x, y, z in F, they satisfy the association associative property, right? So x plus y in one bracket, that is, you perform your addition with x and y first before you add z to it, and then you can also add y and z before you add x to them, and any way you do it, you get the same thing. Okay, so these are the properties that are supposed to have, and for all x, y, z in F, that you have distribution property here. X times y plus z is the same as x times y, and then plus x times z. Notice that these are fields, so I'm talking about numbers. Okay, so you can think of a field as just a set with just numbers. Okay, there's an element 0 such that for all x being in F, x plus 0 is the same as 0 plus x, and it's equal to x. And then the same thing happens to 1. When you have 1, x times 1 is the same as 1 times x, and is equal to x. Okay, I mean, these are basic things. I'm sure you know these by now, but they are very important for study of linear algebra, and especially in vector spaces. Okay, now let's go to the next one. The last property is that for all x in the field F, there is an element negative x being in F such that sum of x and it negative, that is negative x plus x, and then x plus negative x will give you the identity 0. I didn't mention that, but the 0 here is the additive identity. And on the other hand, we have x times x inverse equals x inverse times x, and that is equal to the multiplicative identity. And this property works for all elements in the field F except 0. Okay, so you should take note of that. If F is a finite field, we say F is finite. If it's not finite, we call it infinite, and those things. So let me just give some example. An example of the field is the real numbers, the complex numbers, rational numbers. So why is the real numbers a field? It's a field because if I have 1 belongs to the real number, and then if I have 0.5, it also belongs to the real numbers, right? And I know 1 plus 0.5 is the same as 0.5 plus 1, and that's 1.5, and that belongs to the field, so which is R. Okay, so you go back and you realize that if you pick any two numbers in the real numbers, they belong to they satisfy all these axioms I've mentioned. Okay, on the other hand, if you pick a complex number, the same thing happens to that. In terms of rational numbers, same thing happens to that. But know the definition of rational number is any number that can be written as p over q, where p and q are both integers, and that q is never 0. Okay, now a field of order, so the other example I can also talk about is a field of order p where p is prime. So in that case, all of the elements in that field is given by 0, 1 all the way to p minus 1. What I mean is, if I choose p to be 3, then f3, the field f3 is equal to 0, 1, 2, right? So the last element is p minus 1, and this p here is 3, so I have 3 minus 1, that is 2. And here you realize that every operation you do, the addition operation and then the scalar or the multiplication operation here, is done in modulo p. So here p is 3, so if I pick two elements like 1 and 2, 1 plus 2 is equal to 3, then I have to perform it in modulo 3, which will give me 0. And that 0 also belongs to the same field, p, okay, fp, okay? So, I mean, these are some examples I can talk about fields, and like I said, they are just the basic foundation for, how do I call it, vector spaces. So what is a vector space then? A vector space V over field F, so that is why it is so important, because we define a vector space over a particular field. So we choose a field and we define that vector space over that. It's a set equipped with two operations. So you have addition that maps elements. So you pick an element in V cross an element in V. What this cross here means is not multiplication. What it means is I'm picking an element in V and I'm performing it on, or maybe I'm doing something together with another element in V. Okay, so it goes to, so V cross V goes to V, and what it means is I pick an element, let's say a vector X in V and a vector Y. Notice how I'm denoting the X and Y's in this vector space. In the field, I was just representing them by just normal X without any bar on top of them. Okay, so these are vectors, and in that case, when you sum them, X plus Y, these are vectors, you're gonna get an element in V. So when you sum them, you get an element back in V, the set you're talking about. Okay, scalar multiplication, you have a field, an element in the field cross an element in the vector space, or the set that we are considering to be a vector space. Then what it means is I'm going to pick some value or some number in the scalar field, say A, and a vector in the vector space V, and that vector I'm calling it some small x. Okay, when I multiply A and X, I'm going to get an element back in V. So these two are very important. Then if you have a set that is equipped with this and it's satisfying the following properties, the vector space axiom 1, so VS1, x plus y equals y plus x. Here x and y are vectors. For all x in V, x plus y, before that you add them and you add z to it. Same thing as doing that here. So associative properties again here, they are the same. And then if you have a zero vector in V such that x plus 0 is equal to x, or is equal to 0 plus x and equal to x for all x in V, VS4 saying that for all x in V there is a y in V such that x plus y is equal to 0, and that is the inverse of x in this case, because the additive identity for field and vector space is 0, right? And you have 1 belonging to the field, and for all x in V, 1 times x is equal to x, and that is the multiplicative identity for vector space. Okay, that is the one. For all a b in the field F, and for all x in V, a b, that is before you multiply a and b first before you multiply them to the vector. It's the same thing as multiplying one of them first to the vector, and then you multiply your result by the scalar again, the other scalar, that's the a. If you have a going into this, you can distribute that and you have ax plus ay. If you have a plus b into x, you can do the same thing, as plus bx. And all these, when they are being satisfied with a particular set that you define, then that set becomes a vector space. Now let's pick an example. I'm saying that the R2 is a vector space. In fact, before I start with everything, you can call R1 or maybe R as a vector space. In that case, every vector you pick there is just a one-dimensional vector, right? So you don't have any other way. It also a field, so I don't know, but you can think of it that way, that R1 is actually a vector with just one dimension, and it's also a field. Okay, so now let's go to the R2. Why am I saying this is a vector space? In fact, if something is a vector space, there are two things. If you can show, then you are done. Now, for any general element in R2 is being given by a comma b, belonging to R2, and here I'll state it clearly that this is defined on the field R1. Okay, the reason is, when I say it's defined on the field R1, then it means these elements will belong to R1, and that is the real numbers. Okay, this also belongs to the R1. So in that case, if I can show addition. Okay, so if I add any two elements, let me pick another element, say CD, I'm going to have A plus B, and then A plus C. Actually, that's how you add vectors, right? B plus D, and this will sum up and give you some value here, and this will sum up and give you some value, and that belongs to R2. So you still have some addition of two vectors being in the vector space or the set R2 we are talking about. If you have any scalar, say alpha or something, you can think of multiplying AB, then this is equal to alpha A, alpha B, and this is a two-dimensional vector which belongs to R2, right? So an example that you can pick is maybe the vector x equals 1, 3, and so the vector y equals maybe 4, -2, right? Now if you look at x plus y is equal to 5, 1, which is in R2, right? So that's what we just did. Now if you look at maybe alpha equals, maybe if I choose alpha equals 5, then alpha x is equal to 5 times x, and that is equal to 5 times x will give me 5 times 1, which is 5, 5 times 3, which is 15, and it's still in R2. This is what we mean by these general forms. Okay, so you realize that if these two are satisfied, trust me, you're going to go through all these and it will satisfy. There are some cases it may not necessarily satisfy, but I mean, I'll talk about that when such situations arise. But if you're able to show these two and also show all these axioms together with whatever you've shown, then your vector space or the set given is a vector space. And I'm claiming that this is a vector space. You can continue with showing all these things. If you want to show that the zero vector is actually in R2, indeed, the origin, if you have a two-dimensional, the origin is 0, 0, right? And it belongs to R2. If you add it to any vector in R2, you get the same vector back. Then we can generalize it that then general Rn, so it can be R3, R4, R5, R1, like I said earlier, R16 is a vector space, right? And for this particular one, any element, let's say x, will be given by, so this is also defined on R, the real numbers. This can be given by maybe, let me say A1, A2, some real numbers all the way to AN, okay? And y will be equal to, y will be equal to some B1, B2, all the way to some Bn. If you look at it very carefully, x plus y is the same as A1 plus B1, A2 plus B2, and you sum some things all the way to AN plus BN. And this belongs to Rn, because if you sum them, you're going to get a value all the way, and it's an n-dimensional vector that you have here, okay? If you do a scalar multiple, you realize you have the same thing. So this Rn is also a vector space. You can pick any numbers or any vector you can think of, right? So you can pick A1 to maybe 1, A2 to be 2, 3, all the way to maybe whatever you want to put there, okay? Now I'm talking about the square and 2 by 2 square matrix, and I'm saying that that's also a vector space. And in fact, when you are done with that, you can note that m by some capital M by n is actually a vector space. You can also try to prove that yourself, or maybe try to figure it out. But looking at this, if I want to pick a vector in this one, I'm going to pick an element in this 2 by 2 square matrix, and I'm going to call it x11, x12, x21, x22. If you remember, we've done matrices before, so you know how to go about this. If I pick another element in this, say y, which is equal to y11, y12, y21, y22, then if I sum them, if you're doing matrix addition, you're going to add components to components. So you're going to have x11 plus y11, then x12 plus y12, x21 plus y21, x22 plus y22. And this is also a 2 by 2 square matrix, right? And like I said, if you do the scalar multiplication as well, if you do maybe alpha times x, you're gonna have alpha x11 plus alpha x12, alpha x21, alpha x22. And this is a 2 by 2 square matrix. And if you do it, whatever axiom you can think of, you can actually show it here. And so this becomes a vector space. Okay, like I said, you can generalize it with m by n matrix, and that becomes a vector space. So the question I'm asking here is, if V equals R a vector space over F equals C? That's a question I'm asking. What do you think? And you can leave your comments in the comment section by showing me why, or maybe stating a reason. So, but before that, you have to think of it this way: if V is R, and if I pick, so it's R, right? So if I pick any element or any vector here, will be just a one-dimensional vector. So maybe an X in this vector space, or this V we are considering, will be maybe 1. All right, the value 1, and maybe your Y will be the value maybe -5. Depends on whatever value you want to pick. I'm just picking any element in the real numbers, right? And then if you look at this very carefully, this is 1 plus -5, that is equal to -4. Okay, but it may not necessarily show that indeed this is a vector space, because remember, our field we are considering here is a complex space. So try to think about it this way. If I choose an alpha that belongs to the field, so I'm going to choose a scalar here. I'm saying that alpha is equal to I. Then choose an x that belongs to the vector space V, maybe an x being equal to the number 3, because you are looking at only just real numbers. Okay, and think about this: if you do alpha times x, will it be in V? Will it be a real number? If not, then you can say this is not a vector space. So basically, I've answered the question already, but try to figure it out and give me a comment in the comment section. See you next time. We're going to start with subspaces and go through a lot of stuff in the vector space here. Try to write some basic proofs, get to nullity of matrices, the rank of matrices, and a whole lot. Okay, so kindly stay tuned. Don't forget to subscribe to my channel if you have not subscribed, and see you in our next lesson.